angle and magnitude of a vector. All right, so in this video lecture, our objective, we want to find the angle and the magnitude of a vector when its components are given. Now let's recall, when we use the word components, we're talking about the x and y components. So we're going to be given the x component and the y component, and we want to find the vector's angle and magnitude. Okay? Let's again begin by recalling what we know that's going to be applicable for this video lecture. We know that if we're given a right triangle, that the angle, we can find that angle, theta, using the inverse tangent of the y length divided by the x length, okay, in a right triangle. And we know that in a right triangle has the Pythagorean theorem, and the hypotenuse is equal to the square root of one leg squared plus the second leg squared. So that's one of the things we know. And the second thing we know, go back into some of our trig knowledge, the inverse tangent function, which is indicated usually on a calculator or in writing with a tan with a little -1 as an exponent, returns a degree value between -90 degrees and 90 degrees. Okay, to find the reference angle, which we'll call theta ref, theta sub ref, REF, the reference angle is the positive angle between 0 and 90 degrees. So to find that, we want to take the inverse tangent of the absolute value of this right here, the absolute value of the y length divided by the x length. So we want to find that reference angle, which we'll then use to come up with the standard position angle in the particular quadrant we're talking about. Okay. So when we're given the components of a vector, again the x component and the y component, and the vector is not in the first quadrant, okay, finding the direction requires first finding the reference angle. That's why I spoke to this up here to remind you, and then using that reference angle and the quadrant to determine the standard position angle we're talking about, that angle theta. Okay, so let's take a look here. Let's do a couple of examples to see how this works. Okay, so I think I got it straightened out. Given the components r sub x is -0.98 and r sub y is 2.56, find vector r's magnitude, r, and standard position angle theta. Okay, so let's draw a picture here. So I'm going to draw my coordinate plane. So here we are, coordinate grid, x and y. Okay, r sub x, so the x component of our vector is -0.98. So it's going off in this direction, okay? And this magnitude is equal to -0.98. Okay, the magnitude of the y component is 2.56. The y component is on the y-axis, so I'll darken in a longer vector. And the magnitude, r sub y, is equal to 2.56 of the y component. Okay, so we know these are the components of a vector, and if we draw this rectangle in this case, we know that the vector we're talking about, and that's a little sloppy. Let's see if I can't do a little bit better to make a straight line. That's better. This is the vector we're talking about, and this is our vector r, and we want to find its magnitude, r, and we want to find this standard position angle, theta. Okay, remember standard position means from the positive x-axis in the counterclockwise direction. Now we can also, I drew it so we can see it. Notice here, however, that because the x component is negative and the y component is positive, we know we're in quadrant 2, because in quadrant 2, the x component is negative and the y component is positive. So we know we're in quadrant 2, and this picture also shows it to us. Okay, so let's find the magnitude. Okay, and we're up here. Whoops, let me come up here a little bit, and we know that we use the Pythagorean theorem to find the magnitude. Okay, the magnitude of r is equal to the square root of, well, in this case, our legs are called x sub x and r sub x, and r sub y. Okay, so the magnitude of this, if we draw a right triangle, this is r sub y, this is r sub x, and we'll come up with the magnitude of the hypotenuse here. We're going to use this, okay? And so r is equal to the square root. Well, r sub x is right here. It's negative 0.98. R sub y is right here, 2.56. Okay, so we have the leg squared plus the leg squared, square root of the sum. Put that into a calculator, and the magnitude of the resultant vector is 2.74. Okay, now let's find this angle, theta, the standard position angle, theta. Okay, we're going to use the reference angle, and I talked about that right here. Okay, we're going to find the reference angle, and then we're going to use the quadrant it's in to determine what the standard position angle is. So, let's do direction. Theta reference, okay, is equal to the inverse tangent of the y length divided by the x length. Well, we can replace that. The reference angle is the inverse tangent. Well, the y length is r sub y. So let's replace that with r sub y. The x length is r sub x. Okay, so we can replace y length with r sub y, x length with r sub x. And we're going to find that reference angle, so theta ref. Okay, well, the inverse tangent of r sub y is 2.56. R sub x is negative 0.98, and we want to find its absolute value because we want to find that reference angle, which is between 0 and 90. Okay, so the reference angle, pop this into a calculator, and we're going to come out with 69.1 degrees. That's the reference angle. Okay, now, we know from our picture here that we're in quadrant 2, and we know that r sub x is negative, r sub y is positive, so that tells us also that we're in quadrant 2. And so to find the standard position angle, we're going to have to take 180 degrees and subtract 69.1, and we come up with 110.9 degrees, and that's our reference angle. And from our picture, we see that we're greater than 90, less than 180. We're in quadrant 2, so this makes sense. Okay? So let's, so we know, find r and theta. We found the magnitude of our resultant vector, 2.74. We found its standard position angle of 110.9 degrees. So our resultant vector r has magnitude, which of course is the r without an arrow over it, of 2.74, and is directed at a standard position angle of one. Oops, I want to include that is it's theta of 110.9 degrees. So there you have it. There's an example using the components, which we know are going to be along the axes, to come up with the vector's magnitude and direction. Let's do one more example. We'll have a vector that'll be a resultant vector that'll be in quadrant number 3. Okay, so give me a second to set myself up. Alrighty, I think I'm where I want to be. Okay, example number 2 here. Okay, given the components. Okay, so we have a vector R, its components, its x component, its y component. The x component is negative 729. The y component is negative 209. Find the vector's magnitude and standard position angle. Okay, let's draw it. So, x component, here's my x and y, my coordinate plane, my rectangular grid. The x component is negative 729, so I go out this way, and I'll go to here. That's x component. So r sub x, the magnitude is negative 729, which means it goes to the left. R sub y is negative 209, so not quite as long. I'll go like that. Again, we're not looking for perfection. The magnitude of the y component is negative 209. And so again, we know that when we add these two up, we'll get the resultant vector. And this is the resultant vector r. Okay, so resultant vector r has an x component and a y component. The x component's magnitude is negative 729. Of course, it's on the x-axis. The y component's vector has a magnitude of negative 209, and of course, it's on the y-axis. And you can see here again, we're going to be in quadrant 3. Okay, so we're going to be between 180 degrees and less than 270 degrees as our standard position angle. If I go like this, that's my theta. Okay, and you can see here the x is negative, the y is negative, and that also indicates we're in quadrant number 3. Okay, so let's go ahead and do a magnitude and direction on this one. Find the resultant vector's magnitude and standard position direction, standard position angle. Okay, magnitude. Well, we know that the magnitude of our resultant vector is equal to the square root of leg squared plus leg squared. Well, our legs are r sub x and r sub y. So r sub x squared plus r sub y squared. And let's just continue on to do some substitution. R sub x is negative 729, so negative 729 squared. R sub y is negative 209 squared. Pop this into your calculator, and out should come 758.4. So that is the magnitude of this resultant vector right here. Okay, let's find the direction. Okay, we know we're looking for the reference angle, and then we'll adjust that for the quadrant. So theta ref is equal to the inverse tangent of the absolute value of the y length over the x length. Opposite over adjacent. Okay, so theta ref is equal to the inverse tangent of negative 209, that's the y length here, over negative 729. Whoops, get my handwriting going here. I can pop that into a calculator. Theta ref comes out to be 16 degrees. The reference angle is 16 degrees. Okay, but we know r sub x and r sub y are negative. Right here, they're both negative, so we're in quadrant 3. And again, we can see that in our picture we drew. We're in the third quadrant, quadrant 1, quadrant 2, quadrant 3. So that means that theta, the actual standard position angle, is equal to 180 plus 16, or 196 degrees. Okay, let me come up a little bit here. All right, so we found r and theta. This is r, the magnitude of our resultant vector. This is the standard position angle theta. Okay, and so I'm going to write that down again. The resultant vector r has a magnitude of, magnitude r of 758.4 units from here, and is directed at a standard position angle. I can't write quite as fast as I can talk, of course. And that's going to be theta of 196 degrees. So there we have it. I want to point out two things that are going to be useful in the next couple of video lectures. We're going to need to know this one, and we're going to need to know this one. We kind of came up with in this video lecture that the magnitude of the resultant vector is equal to the, we use the Pythagorean theorem, it's the square root of the legs, the sum of the legs squared, r sub y, its components squared, excuse me, and that the reference angle is the inverse tangent of the absolute value of the y component divided by the x component. So put some boxes around those. We'll be making use of those in our next video lecture.